Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 29, 2026, just yesterday. It introduces a framework called Scout, which enables a QN 2.53B model to achieve an average score of 0.86 on unseen tasks, effectively beating proprietary models like Gemini 2.5 Pro while reducing GPU usage by about 60%. The paper is titled, Language-Based Trial and Error Falls Behind in the Era of Experience. And as we'll see shortly, the strategy of decoupling exploration from the main language model offers a really promising path for efficient training. And for those interested in the implementation, the authors have shared their code on GitHub. Well, Figure 1 illustrates the performance gap on two tasks, Sudoku and Sokoban Box 2. In the top panel, the blue line for standard reinforcement learning flatlines near 0, showing it cannot effectively explore the search space. In contrast, the red curve for Scout rises sharply. It gets an initial boost from the exploration and distillation stage, then climbs to nearly 100% during the evolving stage. The bottom panel confirms this, where Scout quickly locks in skills that the baseline model completely misses. So, Figure 2 lays out exactly how this framework achieves those gains by splitting the process into three distinct stages. First, look at the exploration stage on the left. It uses lightweight Scout models, tiny neural networks, to interact with the environment and collect trajectories cheaply using standard reinforcement learning. Then, the distillation stage in the center converts those raw experiences into dialogue via a textualizer, using them to fine-tune the large language model. Finally, the evolving stage on the right applies multi-turn PPO to this warmed-up model, enabling it to refine its reasoning and master the task. Alright, since Figure 2 outlined the method, Table 1 now presents the comprehensive results across 6 unseen tasks. First, notice the small neural networks at the top. These tiny Scout models achieve a remarkable average success rate of 0.83, setting a strong baseline for the larger models. Moving to the QN 2.53B results in the middle, the performance jump is clear. The base model starts at just 0.18, but the full Scout pipeline boosts this all the way to 0.86. By contrast, looking at the proprietary models at the bottom, even Gemini 2.5 Pro only reaches 0.60, showing just how effective this training strategy is. Okay, moving from performance to cost, Table 2 highlights the massive resource difference between the main models and the Scouts. The first row compares hardware. Large language models require high-end GPUs, whereas the Scouts run efficiently on standard commodity CPUs. Looking at the parameter size and memory rows, the contrast is stark. The Scouts are about 100,000 times smaller and use less than 1 GB of RAM. This decoupling means the expensive trial and error phase becomes GPU independent, as shown in the efficiency gain column on the right. So, Table 3 translates those hardware specs into actual training costs for the Rubik's Cube task. First, look at the direct PPO baseline in the top row. It consumes 24 GPU hours on an 8H100 node because the heavy model does all the exploring. Now, contrast that with the Scout method below. The exploration stage uses 0 GPU hours because it runs entirely on CPUs. Consequently, the total cost drops to just 9.6 GPU hours, representing a 60% reduction. Well, Figure 3 shifts the focus from efficiency to stability, testing if the model can learn a sequence of tasks without forgetting previous ones. On the left, the standard sequential RL baseline struggles. Notice how the blue bandit line fluctuates, and the purple Sudoku line stays near 0 until the very end. In contrast, the Scout results on the right show a dramatic difference. Thanks to the distill stage, performance on all tasks jumps immediately. See how the blue and orange lines hit near-perfect scores right away. Crucially, as the model trains on new stages like Rubik's Cube or Sudoku, it maintains that high performance on earlier tasks, proving it avoids catastrophic forgetting. Wrapping up, 2 takeaways stand out. First, the Scout framework demonstrates that offloading exploration to tiny, efficient Scouts yields better performance at a fraction of the cost. Second, this decoupling provides a scalable path for grounding AI in the physical world, solving symbolic tasks where pure language reasoning typically fails. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.